All right, so we kind of left off, and hopefully after reading and taking notes on the lecture and looking at notes again, some of this is clear, but examples usually are a great way for illustrating some basic stuff, right? So let's take a look at 5.28. This is a chapter problem, and this is on page 230. So for this question, right, we're talking about recidivism. So classic criminal justice problem. So for this question, it's asking recidivism rates is defined as being reincarcerated within 5 years of being sent to jail initially. Among the data reported, Business Insider cites that the recidivism rates for blacks is 81%. So recid for black, African American, and Caribbean American people. And also, we're also looking at recid for white people. And so for this one, real quick, so what it's asking, using notation, express each of these as a conditional probability. So the way this is, so the first one, what it's asking is, what is the probability of recidivating given, note that vertical bar, that you are black or African American or Caribbean American? And based on the information here, it says that this is equal to 0.81. Now, if we go back to white people, it's asking us what is the probability of recidivism given that you are white. And this, according to what's available here, is 0.73. So based off of this, right, so this is the way that we would annotate it. We'd make those markings, right? And so we saw that the recidivism given someone's ethnic background is this. And, you know, if we like added on real quick, a little mini conclusion that is not related to this, we would say that within 5 years of release, black, African American, or Caribbean American people have a 8% greater likelihood of going back to prison than white people released from prison. Right? So that one, pretty easy, right? So far, we feel like we have a good handle of this whole probability thing, right? Conditional probability thing. So let's move on to a different one then. So one that may be a little bit more challenging, but I still think that we can do. And so we'll do 5.32. And this is on page 231. And so this one is asking about cancer deaths. So it says current estimates that are about 25% of all deaths are due to cancer. So we have death because of cancer is 25%. And so, and of the deaths that are due to cancer, right? So due to cancer, so these people we know already have cancer, right? And so, and of the deaths that are due to cancer, we find out a couple things, right? So one, tobacco says that this is 30%. And two, we have diet. So poor diet, that is 40%. And other, which is 30%. So what this is asking us is that the define events and identify which of these four probabilities refer to conditional probabilities, right? So this seems like, what's going on, if we think about this, right? So how do we go about this, right? So let's look at how we would answer that first part of the question. So first part of the question that we look at, right, like we look at, there are, really, when we think about these deaths that are due to cancer, right? So we have one, which is C, and we'll say that this is cancer, right? And we know that there is tobacco-related deaths, which is tobacco. We know that there are ones due to diet, which we'll call D. And we know that there are other causes, O for other, right? And so what it's saying is, so we have these four different ones, right? So which ones are going to be conditional, right? So there are really three possible events here, right? So all these people have cancer, but it really depends on how you died, right? So these last three, what we're end up saying, right? So the answer to what this is going to be, right, is that if we have a cancer death due to tobacco is one conditional probability, right? And again, this is 0.30. We have a cancer death due to diet, which is 0.40. And we have a cancer death to other, which is equal to 0.30, right? So these right here, so the cancer is just like an event, right? But the conditional, so cancer and have cancer, it's attributed to tobacco, that is the conditional probability. Or you have cancer and it's attributed to the diet, that's a conditional probability. If it's a cancer death, and then it's for other causes, like that's the conditional probability. And so what is part B asking us? So we think about part B. Find the probability that a death is due to cancer and tobacco, right? So this is an intersection question, right? So what this is asking us, like what is the probability of the death of cancer and tobacco, right? So a different way to think about this is if we move to a different color, to move here, right? So this is a conditional probability. So basically what we're trying to find, oops, I didn't want to draw that. Drew a perfect triangle though. I didn't know you could do that with this. So this is going to equal the probability of tobacco-related cancer. So the probability of a tobacco-related death given that you have cancer times, which is proportional, times the probability of having cancer, right? So this is the way that we would solve this problem. And if we plugged in our numbers here, so we already know that the probability of having cancer-related death due to tobacco is 0.30, and we would multiply this times the probability of having a cancer-related death in general, which is 0.25. I got this information from right here at the start of the question, so this is where I got it. And we would ultimately find that the probability of having cancer and it being related to tobacco is tobacco-related death is 0.075. So basic way to do that, and we'll do a couple more here just for really good practice here, because again, I know this stuff can seem kind of convoluted, And maybe hopefully this is making more sense, but really I'm interested in you guys practicing well and doing a lot, so that's why we do a lot of these examples. So we'll do 5.33, also on page 231. So this one is asking us, so it's looking at seatbelts and auto accidents. And so we're recreating this table, right? So let's recreate this table, right, that we have in here, right? So we have, if someone is wearing a seatbelt, and we have our seatbelt here, we have, yes, they were wearing it. We have no, and we have the total. And then up at the top here, we have the outcome. And on this particular outcome, right, what do we have? We have S, which is the number of people who survived, and D, which is the number of people who died, right? And over here as well, we also have the total. So remember, this is like a contingency probability table, right? That's something that should seem really familiar by now. So we have this, we've drawn our table. And so what do we, if we filled this in, what would we find? So we put in for this first one, 4, 1, 2, 3, 6, 8. For no, 1, 6, 2, 5, 2, 7. And this is going to equal 5, 7, 4, 8, 9, 5. This is 510. This is 1,601. And this is going to equal 21, 1. And this one is going to be 4, 1, 2, 8, 7, 8. 1, 6, 4. 128. And this is going to equal 5, 7, 7. 0, 0, 6. And so because I like to have this separated, I'm just going to go ahead and do that, right? You don't have to do it like this, but this is the way that I like to do it. So this is the information that we're working with for this particular problem, right? So so let's work on number A. So estimate the probability that the individual died in the auto accident, right? So how do we look at this, right? So we know that there are total events that are going on, right? So we know that there are like all these things right here. And we're just looking to find out if someone died. We don't really care how they died or what the causes were. So we're just looking at the dead, and out of total possible events, we would solve this by looking at 2000, or I guess we can do a different color for solving it. Let me erase that. So this would be 2,111 divided by 577,006. And this was ultimately going to equal what? This is going to equal 0.004, right? So pretty small chance that someone died, period, right? So this is not conditional. This is just like the number of total people who died from like this row column by looking here, right? So now we'll move into the conditional probability part. And so it says estimate the probability that the individual died, right? Just for note's sake, right? So this is just the probability of death, period, right? So for B, it's asking us to estimate the probability that the individual died, given that the person wore and did not, and 1 wore and 2 did not wear a seatbelt, and interpret the results. So what this is asking us then is for this first one, right? What is going to be the answer to the probability that someone is dead and they wore a seatbelt, right? dead and wore a seatbelt. So we'll say like, yes, they wore it, right? So that's the way that we have it coded. So how would we end up solving this one? So what we're going to look at here, right, is, so we're going to look at our table, right? We see how we're going to find our dead, right? Then find where this y is, right? And so that we are looking at this number right here, right? So if we're looking at auto accidents, so we find the number of people who died. We're wearing, and yes, we're wearing the seatbelt. So we know that is 510. And we're gonna figure that out of like the total of events, right? So people who were wearing the seatbelt total were 412, 878. So we would divide this as 4112, 878. So I got those numbers here and I got them here, right? So that's how I was figuring out that one. And this is going to equal to about 0.001. So what about part 2? So if we think about part 2 right here, so this is asking a different one. So it's asking, what is the probability of death given that you did not wear a seatbelt? So it's a different question then. So we're still looking at dead people, right? So we'll use a different color. We'll do this orange color. So probability of death. So we're still looking at the death column and did not wear a seatbelt. So we would find here. This is the one that we're looking for. So these are people who are dead and did not wear a seatbelt right here. So this is going to be 1,601. And we'll put a little comma there. Out of total events, right? And so that is right here. So the people who did not wear a seatbelt, total events, is out of 164,128. And that is equal to 0.010. And just for clarification's sake, we'll do that right there. Okay, so hopefully that seems pretty straightforward, pretty easy to figure out with the amount of information. So let's move on to part C. Are the events of dying and wearing a seatbelt independent? Justify our answer, right? So if we look, what is this asking us, right? So if we look at death, right, we see that the probability, we'll use a different color real quick. So we know that the probability of dying, period, right, is equal to 0.04. We know that the probability of dying, given that yes, you did wear a seatbelt, is 0.01. And we know that the probability of dying and you were not wearing a seatbelt is equal to 0.010. So you'll recall that if these were independent, so if independent, these probabilities, the probability of wearing a seatbelt, and dying and not wearing a seatbelt would equal the probability of death. And so based off of this, so how do we find it? So it is, what it's asking is the probability of death equal to the probability of dying given that you were wearing a seatbelt? And is the probability of death equal to the probability of dying given that you were not wearing a seatbelt? And so the answer to all of these, right, is pretty simple, is that 0.004 does not equal the probability of, given that your death, 0.1, and that the probability of 0.004 does not equal the probability of you dying given that you were not wearing a seatbelt. Since these don't equal, so because they're not equal, we cannot assume independence. So hopefully that was pretty good, pretty, somewhat interesting kind of example. And man, I don't know about you, but we're gonna do one more. We're just gonna do one more. Again, you can always pause these videos, you can revisit them, you can rewatch them, rewatch certain sections, so that's always all right. So this will be the last one. So we'll look at 5.37. And this is page 231. And so, let's talk about this triple blood test, right? And so let's recreate this table again. So if someone has Down syndrome, so the probability, so this is going to be D, they have Down syndrome, and D complement, which is not having it. And then we also have this blood test. And so we also know that we can have a positive blood test and we can have a not positive blood test, right? And so go back and we'll just build it like I always do. So we have total, and this is going to be total. And if we start filling this in, so we have 48 people who have a positive blood test and they do have Down syndrome. We have 48 people, 1,307 people who have a positive blood test but do not have Down syndrome. And this is equal to 1,355 people. If we look at negative tests, we see that there are 6 negative tests, but 6 people who do have Down syndrome. And we also have 3,921 people who have a negative blood test and do not have Down syndrome, for a total of 3,927 people. If we add all this up, we have 54 total people here. We have 5,228 people here. And we have 5,282 total people. And so let's make this little graphy graph real quick. There's a little table just to keep things neat. All right, so let's look at number A right here. So given that a test result is negative, right? So we're looking at negative outcomes right here. So this is going to be related to this column. This negative showed that the probability the fetus actually has. So what is the probability that that someone has Down syndrome, even though they have a negative blood test, is equal to 0.00015. So how would we go about figuring this out? So what this is going to ask us to do is to look at how many people actually have Down syndrome given that they have a negative test, right? So we see, we'll pick a different color real quick. So we see that there are 6 people who actually have Down syndrome given they have a negative test. So that's 6 people out of 3,927 people who actually tested negative anyway. So that is 3,927. And this is going to equal about 0.0015, right? Pretty easy stuff. So let's move back to a different question. Part B. So this is asking, is the probability of having Down syndrome given a negative test, is this equal to the probability of testing negative given that you have Down syndrome? So if so, explain why. If not, explain why find the probability of, that you have a negative test given that you have Down syndrome, right? So how would we go about, maybe we should like start finding this, right? So the way that we would maybe figure this one out is that we would look at, we're coming across a different way, right? So it's asking a different question. So if we, like people who have Down syndrome, there are 6 total, given you have negative, right? So 6 total people out of 54 who have Down syndrome anyway. So because we're moving across the column differently, right? So there are different premises. So it's a different way to ask it. And the way that we look at this one right here, we found that this was the probability of having a negative result, different d. So we moved across the column differently, and this is going to be 6 over 54, and that is equal to 0.111. So what this is basically saying is like, one asks us to tell what proportion of babies, right, have negative tests who actually have it, right? And so it's a very small number of people. The other asks us to say how many babies have Down syndrome had a negative test, because this is getting to like a false negative thing, right? False negative issues. And because these are different questions, these are not equivalent. They are not asking for the same thing in general. All right, so hopefully these examples help clarify a few common stuff. I know a lot of it can get easy, but hopefully seeing an example how you go about solving it would be kind of easier. Please work on some of these practice problems as well as the ones that are available on Blackboard. So until then, I'll see you guys next time.